We'll focus first on the quantum materials. So it's interesting to see that each time there was a development in the quantum devices, our ability to execute algorithms, to operate qubits with higher control, this was mainly due to developments in the quantum materials. Materials that provide higher uniformity or have ingredients that allow us for different control. These determined in the end the quality on the devices that we can perform with. And so I envision that also in the coming years, that we'll see again waves of new generations of quantum materials that then will lead to new abilities and better control of quantum devices. So it makes sense to focus strongly on the quantum materials. First, let's start from a historical perspective. In our field, we started with gallium arsenide. Gallium arsenide has been a workhorse for decades for quantum transport measurements, exploring mesoscopic physics, such as the quantum Hall state. However, gallium arsenide is a group V5 semiconductor, and therefore there are isotopes with a non-zero nuclear spin. And these non-zero nuclear spins can interact with the spin that we're later on going to use to define a qubit. And these interactions are so detrimental that the coherence of the spin is heavily reduced. So in gallium arsenide quantum dot qubits, typically the dephasing time can be order of a few nanoseconds to 10 nanoseconds or so. And so therefore there has been a strong push to alternative materials. And this led to a new wave of generations of devices, in particular on silicon. Silicon is the material behind the semiconductor manufacturing. But silicon is also a group 4 semiconductor, and it has an isotope with a zero nuclear spin, particularly silicon-28. And so by defining quantum dot qubits in silicon-28, there was a great improvement of several orders of magnitude in the coherence. However, as opposed to gallium arsenide, which is excellent for charge control, in silicon this is much more challenging. First of all, the effective mass in silicon is quite a bit larger than in gallium arsenide, meaning that our wave functions are smaller and we need to make smaller quantum dots. Also, by confining the electrons very close to the interface of a dielectric means that they're very sensitive to the quality of that dielectric. And so there are challenges in the charge control and the quality of it. And therefore, it's challenging to make arrays of qubits in silicon dioxide where we can couple quantum dot qubits to one to another. As a first step to overcome this challenge, there was a generation of heterostructures, in particular silicon germanium. So by burying the quantum well deep underneath the interface, the quantum dots are not so sensitive anymore to the quality of the interface. However, there's still the effective mass, which is rather large, so we still need to make small quantum dots. In particular, now there's a challenge in silicon to operate these qubits. And one method to do this is, for example, by adding a nanomagnet, which is creating field gradients. We'll see later more on this. The requirement to add this kind of functionality also creates challenges in its scalability. In germanium, this may not be necessary. So first of all, the quality of quantum wells in germanium is rather high. So we have a very good charge control. There's low disorder. Also, in germanium, there's a rather small effective mass. And finally, in germanium, we're typically not using the electron, but a hole as the basis for our qubits. And these holes experience strong spin-orbit interactions, and that provides a knob for all electrical intrinsic qubit control. Now, of course, in this platform, there are also many challenges, and we'll see some of them here, but also many opportunities. And we see a rapid developments in new materials opportunities coming here. And in Ignite, we're exploring some of them, and in this presentation, we'll be addressing a few of them. So first, let's focus a bit more on the novelties and the unique features of germanium. So first of all, there's a low effective mass. There's absence of degenerate valley states, meaning that the excited states of our qubit can be rather large, are limited by the orbital splitting, which can be millielectron volts or larger. Nuclear spin-free isotopes. There's spin-orbit interactions for all electrical qubit control. The qubits are located in the high-quality buried quantum wells. And finally, one can also make an atomic contact to metals. So as opposed to, for example, silicon, where one needs to implant ions to make contact to a 2-deck, in germanium, it's possible to directly integrate a metal into the system. This may be used for novel type of devices, such as superconductor semiconductor devices, but also purely for spin qubits, this is highly beneficial, as it means that, for example, our sensors can be made purely by metals, which have a very low resistance and can be directly interconnected to somewhere in the array.